Hi everyone, my name is Pablo Lopez. I will present the main results of the work I did in collaboration with Mario Cautun, Dante Paz, Manuel Merchan, and Rien van der Beyer on the evolution of the alignment between the spin of dark matter halos and the cosmic filaments, analyzed in the context of the tidal torque theory. The tidal torque theory is the currently most accepted model for angular momentum acquisition of dark matter halos. It has several strengths, such as it provides analytical expressions that allow to make predictions and uh, compare them with the results from numerical simulations. It involves quantities that can be modeled, and that makes it conceptually very interesting. But it has some problems. For instance, that the validity of the model is limited only to the early stages, that is, the linear and quasi-linear regimes in the formation of structure. And as a consequence of that, it is accurate in a statistical sense. It describes reasonably well the median evolution of dark matter halos, as we will see in brief, but it is not accurate. It is not useful to predict the angular momentum of individual halos. So we would like to understand how halos deviate from the predictions of this model. Hence, we would like to address in this presentation a few questions. First of all, what are the actual predictions of the model regarding the angular momentum growth and the orientation of the spin? We would like to see if there's a correlation between how halos deviate from the predicted angular momentum growth and how they deviate from the predicted orientation. And finally, we would like to see if there's a connection between these deviations and the nature of the cosmic wave in which the halos are embedded. Hence, the content of this presentation is organized as follows. I will talk a little about the basics of the TTT and its predictions. Then we will see uh, basics, a basic testing of the predictions of the model in growth and orientation. And then we will try to connect the deviations that we identify in this section over here, uh, in order to analyze how the cosmic filaments affect the dynamical evolution of dark matter halos. So let's talk first of all about the basics of the TTT. The model tries to answer to the question of why do galaxies and halos rotate. For that, we have to locate ourselves in the primitive universe. This is a Friedman-Robertson-Walker universe, which expands according to a scale factor. And here, the large-scale structures that we see today are only small perturbations or small overdensities over a um, otherwise uniform density field. And as these overdensities expand and, and increase with time, they couple with their inertia tensor couples with the tidal field produced by their surrounding perturbations, their neighboring perturbations, and this causes a net torque that eventually induces a net rotation in the protostructure that is forming. This is the basic idea of the TTT, which is neatly summarized in the expression we owe to White, uh, which essentially tells us that the angular momentum of dark matter halos arises as a consequence of the misalignment between the tidal field around a protostructure and its inertia tensor. And it has this separate temporal dependence that depends on cosmology through this factor here, which is the time derivative of the growing mode of density perturbations. Uh, with this in hand, we're ready to make some predictions. First of all, let's see what we should expect for the angular momentum growth. This factor over here in an Einstein de Sitter universe, which is a good approximation for the primitive universe, is proportional to the time. So we should expect the angular momentum to grow in proportion to t, to the cosmic time t, up to the turnaround of each proto-halo. After that point, we expect the angular momentum to remain constant up to the present time, because at this moment halos decouple from the Hubble expansion and get further and further away from the perturbation that were torquing them. Uh, regarding the spin direction, we will have to compare this direction with something. In the large-scale structure, we can use as a reference the directions of the tidal field around each proto-halo. And since the time dependence is the same for all the components of the angular momentum, this expression here tells us that the angular momentum will have a fixed orientation because uh, they will all the components will grow proportionally to each other, and of course some of them will be larger than the others depending on the correlation between these two tensors here. And taking into account the actual correlation that there exists between these two tensors, Lee and Penn in 2000 and Porciani and collaborators in 2001 computed that the spin should be, according to the TTT, perpendicular to the first axis of the tidal field and weakly aligned with the second and third axis. This is, of course, only expected to hold at high redshift when the model assumptions are valid. Okay, so let's test some of these predictions. First of all, we need a numerical simulation. We have this simulation of 400 megaparsecs sided periodic box. We identify using a friends of friends algorithm nearly 500,000 dark matter halos with masses between 10 to the 11 and 10 to the 13 solar masses. And once we have the halos identified, we track their particles back in time up to the initial conditions, where we find this Lagrangian region, and we compute at each time step the properties of the corresponding proto-halos, and in particular, of course, the angular momentum of the proto-halos. So we can track the evolution of the angular momentum and plot something like this. This is the time in the horizontal axis and the angular momentum growth in the vertical axis. We see that the prediction over here is really accurate during the first stages of structure formation. There's excellent agreement in there. But as we approach the present time, non-linearities arise in the evolution of halos, and mergers, flybys, and secondary torques might deviate the final angular momentum from what we would expect from this naive prediction. So that's the reason we have this large scatter over here. So again, we have excellent agreement in this region and a large scatter in the final stages. This is on the spin growth. What about the spin orientation? To compare the spin orientations with the predictions, we will use the filaments as a reference. The filaments are, of course, shaped by the tidal field, and because of that, they are highly correlated with the directions of the tidal field. In order to identify filaments, we use a Nexus algorithm. The Nexus algorithm tells us for a given halo at the present time embedded in a filament, Nexus tells us what are the preferred orientation, the preferred directions of the axis of that filament. We will associate the direction E3 with the spine of the filament, and we will associate the direction E1 with the first axis of collapse of the tidal field of the filament, and hence with the first axis of the tidal field. So what we will maintain fixed the directions of the filament at the present time, and then we will compute the angular momentum at different times of the proto-halos and compare them with the directions of the filament. This is a schematic representation of this process. You can see how some proto-halos evolve and change their angular momentum, which is shown hidden here by the arrows. The direction of the spin changes dramatically. And in other cases, the spin does not change, which is in accordance with the TTT. This is the present day alignment between the spin and the filament axis. You can see here the orientation of the angular momentum, the PDF of the orientation of the angular momentum with respect to E1 and E3. Towards the left-hand side of each plot, we have perpendicularity, and towards the right-hand side, we have alignment. The first we can notice is that the TTT prediction is not very accurate here, because we were expecting, remember, if we recall, perpendicularity with respect to E1 and alignment with respect to E3. This is not surprising, because we are looking at the present day alignment, and we said that the TTT prediction should only be accurate at high redshift. Another thing that we can see here is the mass trend, the well-known mass trend of higher mass halos, more perpendicular to the cosmic filaments. Remember that this is the spine of the filament. So what happened when we look back in time? If we go back in time, for that we plot here the median alignment for different mass beams and at different redshifts. Again, with respect to E1 and E3, we can see here that as we go back in time, the angular momentum is oriented in a way that is more and more consistent, at least qualitatively, with the TTT prediction. We see that with respect to E3 at redshift 80, at high redshift, there is a slight alignment with respect to E3, except for this high mass beam over here. And that with respect to E1, there is the perpendicularity we were expecting. But as time passes, there's this systematic shift towards more perpendicular configurations that, in the case of E3, seems to stop at about redshift 1, where it looks like the configuration was frozen during this time. We'll see that that's not the case. And this systematic behavior happens even during the linear and quasi-linear stages, because we can see that between redshift 80 and redshift 2, there's a significant shift towards perpendicularity. This is something that is not taken into account in the model, even though it happens in the highly linear regime. So it's something that this suggests that it might be that the model might be extended in order to account for this systematic shift. So now let's connect these deviations that we have identified one with another. Again, we have here the spin growth across cosmic time, here across, in versus the scale factor. We have these dots that represent the median value for this small mass beam. And what we will do is to classify the halos according to the present day distribution of the angular momentum growth. We will split the samples in terciles at the present time, and we will use the upper tercile of the distribution as the high spin growth halos and the lower tercile as the low spin growth halos. Again, this is performed in a small mass beam, and here you can see the evolution of each one of those samples. You can see that there's already a shift, there's already a deviation at a relatively high redshift. And when we do this again for each mass beam in the mass distribution, we obtain something like this. So we have our samples of halos with high spin growth and with low spin growth. Let me stress again that this is not the actual angular momentum at redshift 0, but the spin growth at redshift 0, the net angular momentum growth. This is the distribution of the samples in the same filament I showed before. And let's see what happened with the orientation of the spin with respect to the filaments when we split the samples in these two samples. Okay, this is the same figure that we saw before. We have here the distribution, the PDF of the angle, of the cosine of the angle between the angular momentum and the spine of the filaments, and the mass trend represented by the colors. And in the right hand side, we have the same sample of halos splitted in H and L halos, halos with high spin growth and low spin growth. And it's evident from this figure that halos whose spin has grown above the TTT or the median value uh, are typically oriented perpendicularly to the filaments, and halos of the L sample are typically oriented slightly aligned with the filament. This is something interesting because it tells us it suggests what are the preferred directions of the processes that produce these deviations. This suggests that halos that suffer processes that tend to align their angular momentum with the spine of the filaments also tend to erase the angular momentum that they have gained during the linear evolution. What happens if we look at the evolution of this? Because this was only for the present time. When we look at the evolution again, computing the median value of each one of these distributions and plotting them against the mass of halos, we see that for different redshifts, the evolution is pretty much similar, at least up to redshift 1. Low spin growth halos and high spin growth halos have qualitatively similar orientations at redshift 80 at the initial conditions of the simulations. They both start slightly aligned in accordance with the TTT prediction. But as time passes, they both show this shift towards more perpendicular configurations, which we identified in the general population. But this only happens up to redshift 1. Apparently, after redshift 1, the processes that make this sample lose the angular momentum they have gained also tend to realign halos with the filaments. This tells again what are the preferred directions of these processes, and apparently the processes that enhance the angular momentum evolution of the angular momentum growth of halos continue with the tendency of making the spin align in a perpendicular way with respect to the filament. This is probably the most important result of our work. So quickly, the conclusions. We have that for the general populations, the most important result is that halos changes significantly their angular momentum during the linear and quasi-linear stages, even before redshift 2, contrary to the TTT, and that the spin evolves systematically to become more perpendicular to the spine of the filaments in general. However, this only happens up to redshift 1 because at the present time, L halos show a small excess of parallel orientation, and H halos are clearly perpendicular to the filaments. And this happens because at about redshift 1, the L sample peel off for this general trend of perpendicularity with respect to the filaments and reverse it, while H halos continue with it up to the present time. This is all. Thank you very much for your attention.